So let us discuss one of the major advantages of Rolle's theorem. As I already told, Rolle's theorem is the fundamental mean value theorem. So based on Rolle's theorem or using Rolle's theorem, we can derive more generalized mean value theorems. Generalized in the sense they can be applied to more number of functions. So let us discuss about the one of the significant mean value theorem, what is called as Lagrange's mean value theorem, and this mean value theorem is also based on Rolle's theorem. So the statement of the Lagrange's mean value theorem says that if fx is a real valued function defined on the closed interval AB satisfying the conditions. One is fx must be continuous in the closed interval AB. Second one is fx must be differentiable in the open interval AB. So comparing to the conditions of Rolle's theorem, there are three conditions, but here we are using only two conditions, and both the two conditions are similar to the first two conditions of Rolle's theorem. So first condition says that fx is continuous in the closed interval AB, and second condition says that fx is differentiable in the open interval AB. The conclusion of Rolle's theorem differs here. Here the conclusion of Lagrange's mean value theorem says that there exists at least one point C in the open interval AB such that f of b minus f of a is equal to f dash of c into b minus a. I repeat once again the statement of Lagrange's mean value theorem. If fx is a real valued function defined on the closed interval AB satisfying the conditions, one is fx must be continuous in the closed interval AB, derivable in the open interval AB, then there exists at least one point C in the open interval AB such that f of b minus f of a is equal to f dash of c into b minus a. Of course, in the slope form, the ratio f of b minus f of a divided by b minus a denotes the slope of the line joining f of b and f of a. So f of b minus f of a divided by b minus a, it is equals to f dash of c. This is the conclusion of Lagrange's mean value theorem, where the point C lies between a and b, that is a is less than c is less than b. And for the proof of Lagrange's mean value theorem, we construct a function gx on the closed interval AB such that it satisfies all the conditions of Rolle's theorem. In other words, we define a new function. Let us take g of x is equal to fx minus f of a into minus a into x minus a. I repeat once again, gx is equal to f of x minus f of a minus a into x minus a for every x in the closed interval AB. Here the letter big A denotes a constant. And the value of the constant is to be decided such that gx satisfies all the conditions of Rolle's theorem. The value of the constant a is to be defined in this function such that the function gx satisfies all the conditions of Rolle's theorem. As given, fx is continuous in the closed interval AB and derivable in the open interval AB. We may note that fx and the identity function x satisfies both the conditions of Rolle's theorem. So gx also satisfies both the conditions of Rolle's theorem, first two conditions of Rolle's theorem, that is gx is also continuous in the closed interval AB, gx is also differentiable in the open interval AB. Only for the third condition, what is that one? G of a must equals to g of b. For this condition, we need to decide the value of a. So let us consider g of a. G of a is equal to f of a minus f of a minus a into a minus a, it is equals to 0. Now if we consider g of b is equal to f of b minus f of a minus a into b minus a, and this value must be 0 because g of a must equals to g of b, so g of b must equals to 0. So set g of b is equal to 0, that is what we can see, f of b minus f of a is equal to a into b minus a, or we can write a is equal to f of b minus f of a divided by b minus a. And with this value of a, that is f of b minus f of a divided by b minus a, gx satisfies all the conditions of Rolle's theorem. So gx is continuous in the closed interval ab, gx is derivable in the open interval ab, and now with the value of a, g of a is equal to g of b, so all the conditions of Rolle's theorem are satisfied, hence gx must also satisfy the conclusion of the Rolle's theorem. So by the conclusion of Rolle's theorem, there must exist at least one point c in the open interval ab such that g dash of c is equal to 0. But g dash of c is nothing but f dash c minus a. So f dash of c minus a is equal to 0 implies big A is equal to f dash of c. As earlier the a value is decided, a is equal to f of b minus f of a divided by b minus a. Now the second one is a is equal to f dash of c. Combining both the equations, we can write it as f of b minus f of a divided by b minus a is equal to f dash of c. So this completes the theorem and proof of the Lagrange's mean value theorem. So Lagrange's mean value theorem is that if fx is a real valued function satisfying fx is continuous in the closed interval ab, derivable in the open interval ab, then the conclusion says there exists at least one point c between a and b such that f of b minus f of a divided by b minus a is equal to f dash of c.